Hi, this is video number 4 for our course Parallel Programming. And let me remind you first, this is a supplementary video. So this is a face-to-face course. So again, I strongly recommend you to come to class to discuss these subjects in a longer period of time. Today, our subject is a problem which is called race condition. Race condition. And before we start, I'm going to show you a website which we can understand what happens when we run our Python code. So just run our web browser, and the URL of this website is gotbolt.org, and it's a compiler explorer. What does it mean? Let me switch the language to Python first. Python. All right, and just delete this code. And I just want to initialize a variable with a value, for example, just 0. Then all these four steps, has happened in our CPU. So our interpreter produced these CPU words to run on our CPU. So it starts with a comment load, which is called load constant, with the value 0, and then store this value in a variable which we gave, in a variable name which we gave, which is x here, and then return with a value. All right. So initialize a value and return this value. Let's just increase this value by 1. So I'm going to add a new line with the comment just plus and equals 1. So it increases the value of x by 1. So now we have two parts. The first part is here for our first line, x equals 0. So we have a value which is 0, and then store this value in a variable named x. All right. So just this line includes these two steps in our CPU. But this line increase the value by 1, then in our CPU, all these things happen. So we are going to load a name x, so get the value of x, obviously, and then load a constant, so generate a new value, which is 1 for this case, and then add something to this value, and then store this value in a variable. So to just increase a value by 1 includes these 5 steps. All right, let me do it again. For example, just assign a new value to our variable x. For example, let's say it's going to be equal to 7, and then see the result. So this line 3 produced these 4 steps: load constant, store name, and load constant again. Right? So it just generates the value 7 and then store this value in a variable x. And then let's increase this value by 5, for example, to see clearer. All right. Then all these steps has happened in our CPU. All right. So to understand this, for example, in more than one thread, so we can roughly, so just delete these writings, we can roughly split this process into 3 main parts, right? So to change the value of a variable in a multi-thread program, for example, let's say in this direction, time is advancing, so we have here a thread 0, for example, here, and let's say we have 3 threads, thread 1 and thread 2, so it makes 3 subthreads. And also, let's say for this column we have our main thread. All right, so at the beginning we have our variable x equals 0. So to increase this value by 1, so a thread will get this value, get the value of x, and then change the value, for example, increase it, or we can just use the word change, and then assign the new value back to our variable x. Assign, right? So it makes 3 sub steps to change a value of a variable. It should get the current value and then change the value to produce the new value of our variable, and then assign this new value back to our variable. So for example, let's say we have separate time steps, separate time cycles, for example. So we can use rows to show it in a better way. So time is advancing in this direction when we go to the bottom of this table. So, and we can just numerize these rows also. T equals 1, T equals 2, T equals 3, 4, 5, 6, 7, and 8. And in one time step, for example, T equals 0, thread 0 will try to change the value of x. For example, try to increase the value of x by 1. So it will get the value of x in this time step, get the value. And here the value is 0 because the current value of x is 0 at the beginning. And then change this value. Let's increase this value, increase the value by 1. So the result is 1, and then assign this value back to x, so the value will be 1. So here in this time step, in t equals 4, x becomes 1. X becomes 1. All right. So here x equals 0, and here in the t equals 4, x becomes 1. All right. For example, when we at the time step t equals 3, thread 1 decides to increase the value of x also. So here in t equals 3, thread 1 tries to get the value, and here we still have x equals 0, and here also we still have x equals 0. So thread 1, when the thread 1 tries to get the current value of x, it will get the value 0. All right, and then increase the value. So it will make 1, and then try to assign the value back to our variable x, which is also 1. So here x, the value of x is 1 again. So it should be x equals 2, but still we have x equals 1. Right? For example, in this time step, thread 2 decides to increase the value of x, so it will get the value as 1, all right, and then increase it to 2, and then assign this value back to x, which is also 2. So here we have x equals 1, and here we have x equals 2. All right. And here, for example, thread 0 again tries to increase the value. So try to get the value and gets 1 for t equals 6 and increase the value, which makes 2, and then assign back to this to assign this value back to x, which is 2. All right, and again x becomes to equal 2. So we have here in this table we have 4 separate increments. So one increment and 2 increments, and here this is the third increment, and here we have the fourth increment. So increment has run 4 times, so we can say we have increased the value of x 4 times, but we have x equals 2, not x equals 4. All right, so this condition is called race condition. This problem is called race condition, and it gives wrong results for our variables. So this is a very big problem for concurrent programs. It can be some programs to read and write something from the database, or something is running on the web. It doesn't matter. It doesn't has to be a calculation. It doesn't has to be a scientific calculation. You can face this problem in any kind of program which runs in the concurrent way. All right. So to simulate this problem in Python, I'm going to create a script which we can use for a bank account. And for example, let's say we have a bank account here, bank account, and we will have 2 separate methods which increases the money with the name earn, right, which increases the money, and also another method with the name spend, which decreases the money, right? And I'm going to create this class to simulate the race condition in Python. So to start, I'm going to define first our class with the name bank account, and of course we are going to define a constructor with the double underscore with the name double underscore init double underscore, and also we can call this double underscore with the name dunder. Sometimes we can use this term for this double underscore character, so dunder init dunder. And I'm going to first initialize a balance for our bank account with the value 0, of course, and then let's create our methods, first with the name earn, and the second method with the name spend, and also we can use another method to get the current balance with the name get balance, which returns the current value of our variable self.balance. All right. So in the method earn, I'm going to increase the value of the balance by, for example, 1. And in the spend method, I'm going to define the opposite thing. So self.balance will will be decreased by 1. All right. So if you run this script directly, so name will be equal to thunder main thunder, and then I'm going to create an instance to this class with the name bank underscore account to our class bank account, and I'm going to run this earn method just once. So bank account dot earn and then run spend methods once bank account dot spend and get current balance by using the get balance methods, and then print this balance to the screen. Current balance. I think it's okay. There's no problem, so I'm going to run this code now. Alright, of course we got the value 0 for our balance. So now let's here, after we increase the value of balance, I'm going to print something, let's say earned, and here let's say spent, like this. Alright, let me check it. It runs without a problem. So now I'm going to do the same thing by using the threads. So I'm going to create 2 subthreads, one for the earn method and one for the spend method. So first I'm going to import our thread class from the threading library. So from threading, import threads, and here I'm going to add a thread here. So thread 1, let's say just thread 1, will be equal to thread, and target will be our earn method from the bank account instance, and we don't have any arguments for this moment. So we can delete this line now. Let's do the same thing for the spend method. So thread 2 will be equal to will be an instance to our thread class. So targets will be equal to bank account dot spend and no arguments. Alright, let's delete this one also. Now let's start these 2 threads, thread 1 start, and then thread 2 starts, and then let's wait until the thread 1 is completed by using the join methods, and then do the same thing for thread 2. So thread 2 dot join. Alright. Alright, let's try it. It runs without a problem now. So now we just have not just a single thread script, we just have 2 subthreads. One is for the earn method and one is for the spend method. But now I'm going to increase the number of the increment and also the number of decrement. So in the earn and spend methods, I'm going to add a loop inside these methods. So let's say for underscore, because I won't use the index from this loop. So let's say in the range 1000, for example. So we are going to increase the balance 1000 times. So let's do the same thing for the spend method. So for underscore in range 1000, decrease the balance by 1. Alright, now let's try this version of the code. Again, we have 0 balance at the end, but now, I'm going to change the number in the loop. So let's use 1 million instead of 1000, and let's see the result. And we have a different result now, but we should have 0 because we just call this command self.balance plus n equals 1 1000 times, and we did the same thing in the spend method 1000 times. So it should be equal, and we should have the result as 0, but we don't have it now. But instead of it, we have minus 200,000 something, 240,315. So this is the problem race condition, and to solve this problem, I'm going to use a primitive from the library threading. So here in these 3 sub operations, so this is just the one operation. Self.balance plus n equals 1 here, but it has these 3 sub operations: get the value, increase the value. So our processor gets the value into its register and then increase the value, change the value, and then assign this value back to our variable self.balance. Assign. So these 3 operations should be atomic. So we call this kind of operations atomic operations. So it means non-dividable. All right. So it means you cannot divide. You cannot divide this operation. All right. It's non-dividable. So it means when we try to change the value of x here in the thread 0, it should use a lock. All right, use a lock here. It should acquire a lock or activate a lock. So it means I'm going to change the value of something. I'm going to do something. Please don't do anything. And it must say this to the other threads. All right. So other threads can understand. So it's not the correct time to change anything in this code. All right. In this process. So we should use a lock here when we start an atomic operation like this. So it starts with the get method and then increase the value and then assign this value. So all these 3 time steps starts with the t equals 0 and ends with t equals 4. Other threads should not do anything, must wait. All right, just wait. Don't do anything. I'm going to change the value of something. Please wait for me. It's an atomic operation. It's a non-dividable operation. Please wait for me. So the thread 0 will activate a lock, and then after it finishes the job, after it finishes the atomic operation, then release the lock, and then all the waiting threads, all the other threads which are waiting for this lock can do the job. All right. So now let's delete this part first. Now let's introduce the locks from the threading library. So now with the thread class, I also import the lock class from the same library, from the threading library. And before we use a lock, I'm going to introduce it. So I'm going to use another variable, another property of this class, bank account. So I'm going to use the name lock. So self.lock will be an instance to the lock class, like this. All right. So we have a lock now. We can activate it or release it when we use atomic operations. So here, this part is atomic for us. So before we enter the atomic part of this operation, we are going to acquire a lock. All right, acquired. So this command will activate a lock and makes all the other threads in a sleeping position, in a waiting position. After we finish our atomic operations, then we can release the lock like this. So we should do the same thing for our other methods spent. So self.lock acquire before we enter the atomic operation here, and after we finish this atomic part, we are going to release the lock. So we are ready. Now let's try our code now. At last time we have these results, but now we should have 0. All right. So we get the correct result, and we get our bank account as 0, and also we can increase. Of course, it takes some time, but we can increase this value up to 10 millions, for example. Let's try with this amount. Let's wait for a while to see the result. And in the previous videos or in the previous lectures of our course, we don't face a problem like this, a race condition, because we have the same result, 0 with the 10 million, and we don't face this condition, or we have solved this problem in another way. So we just use the object-oriented programming to solve this course, and I think this is the most reliable way to avoid the race condition. But if you don't have a chance to change something in the code, or if you try to parallelize the code which is written for which is written by the other developers, so maybe you cannot change something and you cannot make it object oriented in the correct way. So you should use locks in these kind of situations, right? Because it will make your code slower, but also it will make your code safer, because it's a strange problem. You don't face it in your local development environment, but you should face it in the running time. So because it isn't a problem when you use this limit as 100 or just 1000 or 10,000, but it becomes a problem when you use 1 million, 10 millions. All right. So this is a very strange problem, but this is a very special problem. You should be careful about the race conditions. But if you use locks a lot, it becomes with a problem also. What happens? For example, in this problem, in this bank account problem, we just have, sorry, all right. In this bank account problem, we just have one resource, which is self.balance, our account balance. All right, we just have one resource, but sometimes we can have more than one resource. For example, we can have, so for any resource, we should have a different another lock. So for example, let's say we have a resource here, resource 1, and let's say we have also another resource, resource 2. So we should use lock 1 here and also lock 2 here, right, to make it safer. So we can have also 2 users to work with these resources. So activates this lock and then releases the locks, 2 separate persons, for example me and my brother, and I'm going to use our names. So for example, Bora and Burak, right? So at the beginning, first I start, so I'm going to activate lock 1, for example, right? First I'm going to activate, so acquire this lock 1, acquire this lock. So let's say this is step 1, and also my brother will acquire the other lock. So this will be a suitable start. So I'm going to start to work with resource 1, and my brother is going to start by using the resource 2. So he will do the same thing, acquires the lock 2, and then when we finish with these locks, I'm going to acquire the lock 2 to work with resource 2. So in the second step, I'm going to acquire the second lock, and also my brother will acquire the first lock now. He acquires this lock in the second step. So it seems okay. Now let's do it in Python. So I'm going to create another Python file. Let's use the name Bora_Burak. All right. So let's use the same methods. So again, we are going to use the thread and lock class from the threading library. So from threading, import threads and lock again. And also I'm going to simulate to do something by slipping. So I will acquire the lock 1. So I will get access to resource 1, and I'm going to do something with this resource. So it takes some time. So I'm going to simulate this process by slipping. So I'm going to import time class also. And we are going to have 2 different methods. One of them is with the name Bora, and the second one with the name Burak. And in the main part, so let's say if under name, will equal to main. All right, let's use the word mutex, and let's say mutex1. And mutex also is an abbreviation, is a very common word, mutex. We are going to use it for it, which it stands for the mutual exclusives. All right. So I'm going to use this name now. Let's say mutex1 will be a lock1. So it's going to be an instance to our lock class. And also we are going to have another class, which is also an instance to the lock class. All right. And we are going to have two subthreads. So I'm going to start with my threads. Let's say Bora underscore threads will be an instance to our thread class with the target Bora. Of course, to make these methods enable to access these locks, I'm going to use two input arguments with the name lock1 and lock2, and also with the same thing in the other method. Let's just use lock1 and lock2. All right, and of course we should give this mutexes as arguments. Let's use mutex1 and mutex2. Same thing for Burak. Burak threads will be an instance thread class. And target will be Burak, and arguments will be mutex1 and mutex2. All right. Now in the methods, now let's say print. Let's make it Bora start with acquiring lock1. So acquiring lock1 and lock1 acquire. All right, and acquire the other lock. Print. Now Bora says acquire lock2 and acquiring the other lock. All right. Now Bora says locks acquired. Now in this state, Bora has the both of the locks. All right. So at the end, once we have the locks, we can release the locks now. So I'm going to release lock1 first, and then lock2, and then let's say print Bora locks released. All right, and then wait for a while. Let's say 0.5 seconds. All right. Also, my brother will do a similar thing, but just one difference. He will try to acquire lock2 first. Lock2, lock1, and then release lock1, release lock2. Sorry, first release lock2 and then release lock1. All right. Change the names. All right. Now at the end we can start the threads. So let's Bora thread start and Burak thread starts. Alright, now we are ready. We have two methods and then we have two logs. We have sent these logs to our methods, so they are going to use them, acquires log 1 and then acquires log 2 and then release both of them, and also Burak will try to acquires log 2 first and then log 1 and then releases both of the logs. So let's try this code. Alright, let's investigate the output. So it just works as I said. Bora gets log 1, Bora gets log 2, and then Bora says I have the logs, and then Bora says I'm going to release the logs, and then Burak has log 1, Burak has log 2, because we didn't change these strings. So this must be log 1, this must be log 2 and 1. Sorry. Just run again to see the correct output. Alright, this is the correct one. So Bora starts with log 1 and Burak starts with log 2 and then gets the both of the logs and then released the two logs. So there's no problem if this method just runs once. So I'm going to make them including an infinite loop. So I'm going to use a infinite loop here by using the while. So while true, run all these codes again and again. So the same thing with Burak. So let's say while true, run all these codes again and again. So we can investigate the output. Let's run our code. It runs and stops in 1 moment. And let's investigate the output. It starts with the same way. So Bora gets the logs, Burak gets the logs, and then Bora get log 1, Burak get log 2. It seems okay. And then Burak try to acquire to log 1 and get the logs and then release the logs. And then Bora here, Bora waits for here. Bora waits for log 2, and when Bora released the log 2, Bora gets it, and then Bora runs, and then release the logs, and then they do it again until this moment, right here. Here, we are in a position, Bora acquires log 2, and Burak acquires log 1, and both of them are waiting for the other log, right? But we are in a position which we can call deadlock. When we have more than one log, like in this problem, the subthreads can be in a position like this. So both of them are waiting for the other log, but both of them don't release the logs. Right? So we should do another thing to avoid the position which we are in now. All right, and we call this problem with the term deadlock. And in the next week, so tomorrow in the class, or next week for you, if you follow the course from the videos, we are going to solve this problem, deadlock. And there's a very famous problem to simulate this deadlock situation. And let me first stop the code. I'm going to kill this process. All right. There's a very famous computer science problem to understand this situation, which is called dining philosophers. Dining philosophers. So this is a problem which we have a dining table and also 5 philosophers. Let's start with the index 0 like we have in Python. So philosopher 0, philosopher 1, philosopher 2, philosopher 3, and philosopher 4. So it makes 5 philosophers, and all of them have their meals on the table. We can call it spaghetti or something else, and all of them will use chopsticks. All right, so we have 5 philosophers around the table and also 5 chopsticks besides the table, like this. All right, these are chopsticks. So we have 5 philosophers. We have 5 chopsticks. So to make all these philosophers eating, we should solve this problem, because a philosopher can be in 2 states, and the first state is thinking, and the other state is eating. So at one time, at the beginning, all of the philosophers are thinking, and at one moment, one philosopher decides to start eat and get one of the chopsticks, and but he or she needs the other chopstick also to eat something. So he or she needs to get 2 chopsticks. But when all the philosophers decide to eat at the same time, all of them gets the chopstick at the left, for example. So philosopher 0 gets this chopstick, philosopher 1 gets this chopstick, philosopher 2 gets this chopstick, and philosopher 3, philosopher 4. Right? And we will be in a position like all of our philosophers have one chopstick, and they will be in a position which they are waiting for the other one. So this situation is called also deadlock. And in the next lecture, like I said, we are going to solve this problem in Python, dining philosophers. All right, see you in the next lecture in the classroom.